In the last video, we discussed various things about the first homology group of a general path-connected space X. This video, we're going to discuss the fact that if we do the complex plane with zero removed, then the homology of this is isomorphic to the integers. Okay, so so we're going to prove that this particular group is isomorphic to integers. That's the kind of first interesting calculation of homology group apart from H0. Okay, and so how do we do this? So the kind of key idea is that as Z moves once around the origin, the logarithm of Z increases by 2 pi I. Okay, so that's kind of how you're supposed to detect that something is moving around the origin. So what exactly do we mean by this? Okay, so I'm going to put there's kind of we have to be rather precise what we mean by the logarithm here. So I'm going to write log with all capitals. So log with all capitals, that just means the set of all possible Z tilde with the property that the exponential of Z tilde is Z. Okay, and there's lots of possible choices of Z tilde. If you've got any one choice, you can add any multiple of 2 pi I to it, and you've got another choice. Okay, what's the usual way to do it? I mean, we can say if Z is kind of R e to the I theta with so R is going to be strictly positive here. I mean, assuming Z is non-zero, so the absolute value is strictly positive. And suppose we take theta in the kind of normal range, so it's going to be like minus pi less than theta less than or equal to pi. So we can always write Z in this form in precisely one way if we restrict the angle to be between minus pi and plus pi like that. So I'm going to put p log Z. That's the principal logarithm. So that's just the ordinary real logarithm of R plus I theta. And so then so this is one choice of the logarithm, and then the general thing is that log Z. Well, you could have p log Z plus any multiple. It's basically capital log Z is a coset. It's a coset. This principal logarithm plus multiples of 2 pi I. Okay, so a key point about this distinction between capital log and p log is like this. If Z is approximately minus 1, then what is what's the principal logarithm or the capital letter logarithm? Well, if Z is minus 1 plus I epsilon with small epsilon greater than 0, then then the principal logarithm is approximately I pi. Because the angle, remember we write this as either R e to the I theta, and in this case theta is going to be approximately pi, but just a little bit less than pi, and so your principal log is like so. And And so log z is approximately the coset I pi plus 2 pi I z. And if z is minus 1 minus I epsilon, again with small positive epsilon. Okay, so here, in the first case, we're looking at a point up here where you've got approximately pi like that, and now we're below the line, and remember we're taking our theta to force it to be in the range between minus pi and plus pi. So in this case, this is approximately minus I pi, but a kind of key point is, of course, these two cosets are actually the same, right? Because the difference between I pi and minus I pi is 2 pi I, which is kind of in this graph. So so these two cosets are the same. So the capital log is not jumping, but the principal logarithm is jumping. So so p log z jumps as z crosses the negative real axis, but capital log does not. So that's kind of how we need to think about this. So let's now consider a path, let's say u, from the unit interval, say, into the non-zero complex numbers. So a continuous log of u is a continuous map. Call it u tilde, from unit interval to the complex numbers, with exponential composed with u tilde equals u, which is the same as saying that u tilde of t is an element of the set capital log of u of t for all t. Okay, so how do we know that there is such a thing? So we first choose x with the exponential of x is u0. So in other words, x is in the capital log u norm. And then so we're going to define u tilde of 0 to be x. Okay. And then we define 0, 1 subintervals. So this is going to be like k over n, so k plus 1 over n. For some suitably large n. Okay. And then and then on this interval, we are going to define u tilde equals t of t as the element of capital log ut close to u tilde of k over n. Okay, so we start. We've defined u tilde of 0. So on the first interval from 0 up to 1 over n, we want to choose ut to be a some possible logarithm, u tilde t to be some possible logarithm of u of t. Now u of t, because n is supposed to be large, and so t as t is on this first interval, it's going to be pretty close to 0. So u of t is going to be close to u of 0, and so you look at log ut, all the possible logarithms of ut. There's going to be a whole bunch of them, and they're all kind of well spaced out, but only one of them is going to be close to our original choice, u tilde 0. So that's what we do on this first interval, and then when we've defined, that gives us u tilde 1 over n, and then we just carry on doing the same sort of thing. Okay. So we'll see this argument in greater detail later in the course, but for the moment I think that's all I'm going to say about it. You just choose your logarithms step by step after dividing your interval into short subintervals, and then that does the job for you. So as an example, you might have a path like this. Here's 0, and then here's maybe your u of 0. And then you've got like u of a half here, say, and then maybe u of 3/4, u of 7/8 there or something, and then yeah. And so this is kind of over to the left. You might have u tilde of 0. This could be -1, say. Then you could take this to be I pi. And as you proceed along to here, then you're going to get this one. You have to choose a logarithm of this, and it's got to increase. So so you're going to be getting just kind of a bit bigger and bigger than I pi. And then when you go over to here, then your u tilde of a half is going to have to be 2 pi I, right? Okay. I mean, all possible logs of this. I mean, let's pretend this is actually equal to 1. Okay, so then the possible choices here. Any even multiple of 2 pi I is a logarithm of 1, but you have to have 2 pi I in order for it to kind of fit together continuously over here. And then you get and then as you get around to here again, let's go all the way over to here, right? So now, as going from here to here, you've gone kind of all the way around, and you're going all the ways anti-clockwise. So the angle is always increasing, and so here is going to be u tilde has got to be sort of real plus 4 pi I. Okay. And then once you go another half turn around, and so you get u tilde of 1 is going to be real plus 5 pi I. Okay. And so the difference here from the thing at the beginning and the thing at the end, the difference between them is 4 pi I, and that corresponds to the fact that your loop has gone twice around. So we can make a definition based on this. So I choose any continuous log u tilde, and then I'm going to put omega of u is going to be u tilde of 1 minus u tilde of 0 over 2 pi I. So for this particular picture thing that we've done here, the change in u tilde is 4 pi I. So this one would have omega of u is 2. And I say I choose any continuous logarithm, but it's easy to see if I have two different continuous logarithms, then they differ by a constant multiple of 2 pi I, and so when we do the subtraction here, it cancels out. So it doesn't matter which choice of continuous log we use. So I've said this in terms of 0, 1. But of course, as usual, we identify 0, 1 with the delta 1. So again, we put omega of u. In this case, it counts as u tilde of E1 minus u tilde of E0. The endpoints in this picture are called E0 and E1. So it's kind of just the same sort of thing. Okay. So now that defines our omega in the context of a single. This is. Remember S1 C cross, that's the set of paths in C cross, or the set of maps from continuous maps from delta 1 into C cross. So we could instead have a chain, M1U1 plus up to MRUR, be a one chain in the non-zero complex numbers. Obviously, we're going to need to consider this group if we're going to understand anything about the homology. And so for this, we're going to put omega of u, and we do the usual sort of linear extension thing, M1 omega U1 plus up to MR omega UR. And notice that we've got a plus on both sides of this equation, but the pluses are kind of these are somewhat different. This is just a kind of ordinary addition of complex numbers. Remember this is an element of C. Whereas this is a kind of formal linear combination. Okay. So I mean, over here, we're not really using anything up, particularly which space we're looking at. We just got not using any algebraic structure of C cross. We're just taking a formal linear combination of points. But over here, we're using the usual sort of algebraic structure of complex numbers to multiply and add like that. Okay, so that's our definition of this map omega. So we just had this map omega here, and we need to combine this with some other maps. Okay. On one hand, we've got this differential. It's obviously important for understanding the homology, and I want to map that I'm going to call gamma here, and map that I'm going to call beta here. Okay, so definition of these, and also let's just remember we've got a differential coming in there as well. So what's the definition? So beta of z is just going to be the exponential of 2 pi I z. So it's a homomorphism in the sense that, here I'm going to regard this guy as a group under addition, this one as a group under multiplication. And so to say that this is a homomorphism means that it converts to sums to products. And the kernel of beta. Okay, so it's the stuff that, kernel beta, that's the things that go to the identity, which is 1. In other words, the things where e to the 2 pi I z is equal to 1. And those are just when z's an integer. So the kernel of beta is the integers. And then okay, so and what about this gamma? Okay, so here a typical element of C0 C cross, that's some kind of formal linear combination of elements of C cross. Okay, and what we do is we just we're going to define this to be Z1 to the M1, Z2 to the M2, ZR to the MR. And so again, this converts sums to products. So usual group structure. This is, well, everything here is a group under addition except for this one's a group under multiplication. So to say that gamma is a homomorphism, oh, sorry, this was supposed to be gamma. So that gamma is a homomorphism means that it converts sums to products, and it does. Okay, so so we've got this diagram here. I want to claim that this commutes. So gamma d of some path u. Okay, so that's gamma of u of e1 minus u of e0. And just by consulting the definition here, so this is you get u of e1 to the plus 1 and u of e0 to the minus 1. So that's u of e1 over u of e0. Whereas beta omega of a path u. Okay, so remember that's the definition of omega. You know, here we're supposed to take a continuous logarithm. We take u tilde e1 minus u tilde e0 divided by 2 pi I. Okay. But then we had to put the 2 pi I back in the definition of beta. So this is the exponential of u tilde e1 minus u tilde e0. But yeah, this u tilde, that's supposed to be a continuous logarithm of u. So the exponential of u tilde e1 is just u of e1. And then because it's taking the exponential of the difference, that's the same as taking the quotient of the differential. So this is u of e1 divided by u of e0. So those are the same. So it's saying the square commutes. So we've got a commutative diagram like so. Okay, so there's another thing I want to add to this diagram. So of course we can. The other thing we can do is to do d followed by omega here, and the claim is that this is 0. Okay. So let's consider some generator of this C2 thing. So this is a map from delta 2 to C cross. So what we're going to, so suppose we're given something like that, then let's just choose x and which is going to be a logarithm of the value at e0, say. So now we're going to try and define v tilde from delta 2 to C. Starting with v tilde of e0 is going to be this x. Roughly speaking, we define v tilde of t is the value in capital log of v of t is close to v tilde t prime for t prime close to t towards e0. So it's more or less the same thing as we did for choosing a continuous logarithm of a path. You know, in the continuous logarithm of a path, you know, you define u tilde of t is it has to be a choice of the logarithm of u of t, and you choose the one that's close to u of t prime when t prime is somewhere slightly to the left where you've already defined your u tilde. So again, we'll do this more carefully when we come to consider covering spaces. So now v tilde So v tilde is a continuous logarithm of v in an obvious sense, and therefore v tilde composed with delta I is a continuous log of v composed with delta I, and therefore omega of v composed with delta I is v tilde composed with delta I v1 minus v tilde composed delta I of E0 all divided by 2 pi I. Okay, but now you just look at this picture here. I mean, here's your delta 2 with your E0, your E1, your E2. And this is image of delta 0. This is the image of delta 1. This is the image of delta 2. So we look at v composed of delta I. Okay, so composed of delta 0. Okay, so that's kind of looking along here, and so you take a value of v tilde at the end point minus the value of v tilde at the beginning point. So that's going to be v tilde E2 minus v tilde E1 over 2 pi I, omega of v composed of delta 1 in the same way. You know, here's your delta v composed of delta 1's here, so you're going from E0 to E2. So here you end up with v tilde E2 minus v tilde E0 over 2 pi I, and the same with delta 2. Okay, so here's the delta 2 thing is like this, going from E0 to E1. So that's v tilde E1 minus v tilde E0 over 2 pi I. Let's call these A, B, and C. And by definition, omega of dv, that's A minus B plus C. Okay, and then if you look at this, and everything's going to cancel out. You've got the v tilde E2 there, cancelling the v tilde E2 there. V tilde minus v tilde E1 here, cancelling with plus v tilde E1 there. And then minus v tilde E0 here, and then this guy comes with an extra minus sign like that. So that term cancels out as well. So you just get 0 as required. This is showing us this triangle here commutes, as I said, omega composed with d as 0. Okay, so now we've got this commutative diagram here. Okay, so what do we learn from this? So let's suppose that Z is a cycle. So we've got Z is in so it's an element of C1. dz is going to be 0. Okay, so then that means that gamma dz, gamma 0 is 0, but the diagram commutes, so that tells us that beta omega z is 0. But remember, the kernel of beta is just the integers, right? Beta was just the map sending t to the e to the 2 pi I t, so the kernel of that is the integers. So we've got so we've got omega of z is an integer. So we've got a homomorphism omega just by restricting that. That goes from the Z1 group to the integers. But also we know that omega d is 0, and therefore omega of B1x is norm. Okay, B1 is the image of D, so we've got anything in the image of D, and it's equal to D of something. So when you apply omega to it, you just get 0 by that commutative diagram there. So we've got an induced homomorphism, omega bar, say, from h1x to the integers. So omega bar of a coset z plus b1x is just omega of z. And it doesn't matter which representative you choose, because the difference between any two representatives will lie in b1x, and so will be set to 0. Okay. Okay, so now we've got this homomorphism omega bar. And the next challenge is to prove that this omega bar is actually an isomorphism. Okay, so where do we stand? We've got this map omega bar we've defined from h1 c cross to the integers. And let's just recall, just restate how this was defined. Okay, so if you look back through the definition, it kind of unrolls like this. I mean, we kind of took a bit of a roundabout route to defining it, just in order to make sure that the definition was well defined. But now that we know that it is, we can just kind of write the formula for it. The typical element here is expressed like this as a some kind of formal combination of so integer linear combination of paths. And for each path, we look at we take a lift, continuous logarithm, UK tilde, and you take the difference between the UK tilde at the endpoints, multiply by the coefficient mk, and divide by 2 pi r. And as we, in the previous video, we proved that any elements of H1 can be represented by loops. Okay, so let's just consider the single case for the loop. And in that case, we just have this to simplifies down. You just get 1 over 2 pi I. U tilde E1 minus U tilde E0. So we could, for any integer n, we can define a particular path, which I'll call Pn. This is just going to be the exponential of 2 pi I n t. Then your obvious choice of lift, Pn tilde 1 minus T is just going to be 2 pi, this thing that we're taking the exponential of. And then from that, we get that omega bar of Pn is just going to be equal to n. Okay. And that proves that our homomorphism is certainly surjective. So we've got this omega bar from H1 C cross to Z. We've shown it's surjective, and we still need to show it's injective. Okay, so we want to prove that omega bar is injective, so we need to consider its kernel. Okay, so so suppose we've got some loop in non-zero complex numbers based at 1. Okay. Okay, so we know that any one-dimensional homology class can be written in that form. Well, it can be written as square bracket u for some such u. Okay, and let's suppose that omega bar of u is 0. Means i.e. u tilde of e1 minus u tilde e0 over 2 pi I is 0. In other words, u tilde of e1 equals u tilde e0. Okay. So this is a continuous log u tilde of u. Okay, so u tilde of 0. If you remember how we did these kind of continuous logarithm, you choose the value of u tilde 0. It can be any logarithm of u0, and then you proceed from there. And so in this case, remember, this is a loop based at 1. So u of 0 is 1, and u tilde of 0 can be any choice of logarithm of 1. So we might as well take u tilde of 0 to be 0. U tilde e0 0. So u tilde of e1 is also going to be 0. Okay. So now I want to define v tilde. It's going to be a map from delta 2 to the complex numbers. This is so remember u tilde is a map to the complex numbers, not including 0, and v tilde is going to be the same. So here this is going to be we have to distinguish the case whether we're at the base point or not. But the normal case is going to be u tilde of t1 over t1 plus t2 or comma t2 over t1 plus t2 or just 0 if t is e0. Okay, so the only case where this first formula doesn't make sense if t1 and t2 are both 0, but if t1 and t2 are both 0, then that means that t0 has to be 1. Otherwise, in other words, you have to be at the bottom, at the corner e0 of your 2 simplex. Okay? So in that case, we define it to be 0. Sorry, and then this is supposed to be multiplied by supposed to take this and I'm supposed to multiply by t1 plus t2, which I don't really have space to write in. Okay, so I take this complex number and multiply it by t1 plus t2. Okay, so because of that, right? As I approach e0, t0 plus t2 or t1 plus t2 will approach 0. So this is going to be continuous. It's kind of obviously continuous except at e0, and then because I put in this factor of t1 plus t2, it's going to be something. Okay. So let's have a look at what happens on the edges of this v tilde. If we do v tilde of 0, t1, okay, so you do v0 0 t1 t2. Okay, so in this case t1 and t2 are necessarily positive. T1 plus t2 is necessarily equal to 1, and so here you just get kind of u tilde of t1 t2. Okay. Whereas v tilde of t0 0 t2, okay, So there you've got U tilde, okay, and then you've got 0, 1. Okay, but that's in other words, U tilde E1, which is 0. And similarly, V tilde, if we do the T0, T1, 0, and that's going to be U tilde 1, 0, U tilde E0, which is 0. So that's the boundary behavior of this map V tilde. Okay, so basically we've got U tilde on one edge and just the constant map 0 on the other two edges. So now let's put V is X composed with V tilde. So that's now a map from delta 2 to C cross again. So kind of reading off from what we got down the bottom, that gives you that this first thing tells us V composed of delta naught is U, and then the other two tell us that V composed of delta 1 and V composed of delta 2 are just a constant map with value 1. So in other words, V is this is a fill-in for U, if you like, but that's just to recall the argument. So you get D of V. Okay, so that's U minus C1 plus C1, which is U. Therefore, U is an element B1 C cross. So conclusion that if omega bar U is 0, then U is in B1, and so square bracket U is 0. Okay. Also, I'll map omega bar from H1x to Z is injective as well as surjective. So it's an isomorphism. So that completes our proof. This is our first. Our first really non-trivial calculation in homology. That the first homology group of the punctured complex plane is isomorphic to Z.